recording.
Okay, so yeah, Chris is laughing at me, but it's not an opening statement like a hearing at the Senate, but it's an opening statement for our students and our community. Today we're here to hear the dissertation defense for Fransiska Dannemann Dugick. The title is Enhancing Infrasound Signal Detection and Event Localization through Advanced Computational Methodologies. I'm going to leave that to her, but I'd like to say some things about Fransiska that probably will resonate with a number of you. She came to SMU in the fall of 2014 from Colorado College to do a master's degree, and which she finished in the summer of 2016. During that time period, she was introduced to infrasound, collaborated with some of our friends at Los Alamos National Laboratory, and then ultimately went on to a position at Los Alamos. I think it was in the fall of 2016. And during that time period, both Omar and Phil were very influential in her work and helped her and became her mentors at Los Alamos. And so when she got to Los Alamos, she decided that she wanted to maybe continue with a PhD. So it was it's been a collaborative effort, which I've been very thankful for with Los Alamos. And so we're here today to hear her results. Most recently, though, she was hired by Sandia National Laboratory in the fall with a permanent staff position, and so I think she should be congratulated. I think it illustrates kind of the growing field of seismoacoustics and infrasound and an interest, which she'll tell us about. But I'd like to say something kind of personal about her. Some things before we begin. She was my TA for a couple years in earthquakes and volcanoes. And one particular semester, we were informed in August that we were going to have a blind student in our class. And she was instrumental in helping us think through how do we do labs and how do we communicate and how do we teach earth science to a blind student, which I think was pretty effective. And he graduated, so that was good. But I think that illustrated to me her interest in people and in her profession. I think that has expanded over the last year or 18 months as she's taken leadership roles in both the American Geophysical Union and the Seismological Society of America, focusing on equity issues, continuing education. She was instrumental in a summer program called ROSES with seismology education in the summer. And so I know that she's going to be instrumental in our community going forward. She has one paper published, one ready to go. She's actually co-author on 5 journal publications. She's got another not to do with her thesis that's in review at Seismological Research Letters. And so she's well underway, I think, in terms of her professional work as well. I'll just end this part, and this is just me personally, but she has always made, I think, us better in a variety of ways. And so with that, Fransiska, I turn it over to you.
Okay, thank you. That was a very nice introduction. So let's see. Everyone can hear me, correct? Okay, great. So I'm going to go ahead and share my presentation here. And okay, we should be able to see my title slide, correct?
Yes.
Okay, Perfect. So the way this is going to go is I'm going to step through my presentation, and then at the end we will open it up to questions. So if you have a question, please wait until the end. I would prefer if you just unmuted yourself and verbalized the question, because I think asking me to also monitor the chat is a little bit too much. So please feel free to unmute yourself and ask a question at the end. Let's see. So, and yeah, I would like to say two things really before I begin. One, I know that doing a defense on Zoom is a little strange, but I actually am personally really grateful for the opportunity to do this. It is really exciting to me that my family was able to join, many of my friends were able to join, and a lot of people who have been with me throughout the 6 years of my PhD career are here to really celebrate how it's gone. And so that to me, I think is a really big benefit of doing this virtually. And I'd just like to acknowledge that I'm very grateful for that opportunity. And then I'd also like to acknowledge that the work that you'll see in this was funded by a combination of grants from Southern Methodist University under Dr. Stump, grants at Los Alamos, and grants at Sandia National Laboratories. And I'm very grateful for all of that financial support throughout my time. And you'll see that I have a number of collaborators listed on different sections of my presentations. And I would just really like to acknowledge and thank them for all of their assistance in the different sections of my 3 chapters I will present today. Okay, so with that, we will begin. Today, I'm going to be discussing signal processing as it relates to signals from sources of infrasound. The field of infrasound is experiencing a renaissance due to its role as one of the 4 technologies utilized for verifying compliance with the Comprehensive Nuclear Test Ban Treaty. The tools for infrasonic signal processing are relatively new, and the analysis is complicated by signal propagation through the atmosphere, which is a changing medium. This presentation will focus on ways to optimally detect signals and locate events, and will draw on years of successful signal detection and event location within the field of seismology to inform some of the practices that we undertake. So to begin, what is infrasound? Infrasound waves are low frequency acoustic waves that we typically observe between 0.1 to 20 hertz, and they're caused by small changes in atmospheric pressure. So seismic and these below audible acoustic signals that we call infrasound are often generated by similar sources. They differ due to their propagation medium. Seismic waves propagate through the solid earth, while infrasound signals propagate through the atmosphere. This distinction is important because infrasound waves are propagating through this dynamic medium, which makes predicting this propagation difficult because your medium is constantly changing. So the motivation behind my thesis work is to develop an understanding of how infrasound signals generated by above surface sources propagate through the atmosphere and are observed at stations within 500 kilometers of a source of interest. So because infrasound is such a younger field than seismology, the research is really focused on understanding and answering fundamental questions. These questions include what sources can be identified, how to detect and locate sources of interest, how to process large volumes of data originating from large networks such as the IMS, how to characterize the time varying nature of the atmosphere and its influence on signal propagation, and how to separate signals of interest from sources of noise. And you'll see that each of these questions will be answered throughout my presentation today. So as I mentioned, infrasound is one of the 4 technologies utilized for verifying compliance with the Comprehensive Test Ban Treaty. The other technologies include seismic or seismology, hydroacoustic, and radionuclide. These 4 technologies combine to make up the International Monitoring System, or IMS, which consists of 337 facilities worldwide that are used to monitor the planet for signs of nuclear explosions. Over 85% of the facilities are already up and running. The infrasound component consists of 60 surface stations worldwide. So the presence of these extremely large networks that are constantly recording data necessitates automated techniques and algorithms for accurate and efficient data processing and analysis. And we'll begin discussing what some of these automated processes look like throughout this presentation. So infrasound can be generated by a variety of sources. These include natural things such as volcanoes, earthquakes, and thunder, or anthropogenic or human generated sources such as aircraft, satellite reentry, or heavy machinery. Another important distinction to make within the field is that what some researchers would consider signals, other researchers would consider this to be noise. So for example, a lot of people are interested in studying the microbaroms, but for me, I consider those to be noise. So this is important when you talk about detection and signals of interest, because depending on what source you're interested in isolating, some things may be nuisance where other people would really consider them signals that they'd like to identify. So within this presentation, I will be focusing on identifying and characterizing signals from above ground chemical explosions. So infrasound, like I mentioned, propagates through the atmosphere, and the waves refract back to the Earth's surface as a result of temperature and velocity gradients within the four layers of the atmosphere. These four layers are the troposphere, the stratosphere, the mesosphere, and the thermosphere. A signal refracts from a layer back down to the Earth's surface when the effective sound speed of the layer is higher than the effective sound speed at the source location. This refraction changes on both a daily and a seasonal basis due to a combination of weather related and so daily changes and then seasonal changes in the atmosphere that primarily affect propagation through the stratospheric duct. So one way that we can model this propagation is using atmospheric models such as the ground to space or G2S model. G2S was developed at the Naval Research Laboratory here in the US and consists of real-time national weather profiles that are combined with numerical model estimates of the atmosphere at higher altitudes. These specifications can be defined by a geographic location and a time. So the speeds of the zonal or east to west and meridional or north to south wind components can be estimated along with the effective sound speed at a specific location. Estimating these components allows us to predict the existence or non-existence of ducts within the layers of the atmosphere for signals to refract off of. So these profiles here illustrate changes in the effective sound speed towards the east and the west at altitude. For an example, summertime wind profile in the Netherlands, and you'll see that signal propagation, the predicted signal propagation changes in these directions, where towards the east, we're only predicting thermospheric arrivals, and towards the west, we're predicting a combination of stratospheric and thermospheric arrivals. So this figure represents a 2D model where we're predicting arrivals just to the direct east and the direct west of a source. The other way that we run modeling is 3D. And so this is an example of a 3D model where we're predicting what types of signals would arrive at all directions from a source. And these colors represent each of the different phases, where red are tropospheric arrivals, green are stratospheric arrivals, and blue are thermospheric arrivals. And so both of these figures illustrate that propagation is variable and changes as a function of time and geographic location. So it's often difficult to identify infrasound signals of interest due to constant noise at the turbulent boundary layer. This noise is due to a combination of factors such as wind or anthropogenic sources such as traffic, airplanes, or heavy machinery. And so in order to observe the signals that we're interested in, we focus on three ways to reduce noise at the sensor. First, we focus on careful site selection and placement into naturally quiet areas such as isolated forests. So this image here is actually a photo that I took at one of the IMS arrays located in Norway. And you can see that the element has been placed within this tall forest to ideally reduce some of the environmental noise. The second technique that we use is we fit individual sensors with noise reduction techniques such as long hoses or pipes. And so here's an example where we have a single sensor here, and you can see there are pipes radiating out from the sensor. And so these act to filter out the amount of wind that you're seeing at a single sensor. And third, we deploy a series of 4 or more sensors at a site. And so this is an example here where this is a single site, and you'll see there are 4 sources, 4 sensors, and these 4 sensors combined to what we consider to be an array. And the reason that we want to deploy arrays is because this allows us to use array processing to extract coherent signals of interest. So what is array processing? Array processing techniques, such as the technique I'll use throughout this presentation called frequency wave number or FK analysis, are used to separate coherent and incoherent parts of a signal through the assumption of a planar wave arriving across the array. The time delays required to bring a single signal into phase provide a direct estimate of the back azimuth, which is the direction from the source to the sensor, and the slowness, which is an estimate of how fast the signal is traveling. So this is powerful for 2 reasons. First, through array processing, we're able to enhance signals of interest and reduce noise across our sensors. And second, we're able to estimate this trace velocity, or how fast a signal is traveling, and a back azimuth, or what direction is the signal originating from. And you'll see these 2 things discussed in more detail throughout this presentation. So what is the real motivation of my presentation here? In addition to the global IMSnet network, a number of regional distance infrasound networks have been installed worldwide. These networks are a relatively recent development, and very little is known about their performance or techniques to produce and evaluate results. The 3 chapters within this presentation will focus on the evaluation of signals from a regional infrasound network of 7 stations, denoted by the blue triangles here on this map, that were deployed in the western US. These sensors were deployed across the state of Utah from 2010 to 2013 and offered the opportunity to evaluate limitations within the field of infrasound at distances between 50 to 500 kilometers from a source of interest. So I'm going to step through 3 chapters here. The first chapter is going to focus on automated ways that we process signals, and we're going to look at identifying how do you identify an optimal detector for your signals. Second, we're going to take a step back and say, okay, now that we've identified an optimal detector, how do we start to physically understand when these detectors are successful and when they fail? And third, after producing an optimal set of detections, we're going to use these detections to locate sources of interest. So you're really going to see as an example of how we move through this automated processing pipeline, starting at signals arriving at a sensor and ending with an event location. So part 1, or chapter 1, is a comparison of common automatic signal detectors. We are going to focus on using signals from acoustic sensors to evaluate 2 automated signal detectors. This is a collaborative study between Los Alamos National Lab and Sandia National Lab that fell under the umbrella of this dynamic networks data processing and analysis experiment that was conducted in 2018. So the real motivation behind this study was that we had outputs generated by 2 distinct automated processing packages, InfraPy, which is a pipeline produced at Los Alamos for infrasound processing, and Bloodhound, which is a similar package produced at Sandia for processing. Each package has its own signal detector, and we ended up with 2 catalogs of results from these signal detectors, and we wanted to find a way to evaluate how do these catalogs compare. And so this work represents a first look at producing methodologies to compare results from different automated detectors. So I'm going to be discussing 2 different detectors and results from 2 different detectors within this presentation. And so one of the common problems in infrasonic data signal detection is that high coherent background noise triggers automatic detectors, which results in false detections or false alarms. The adaptive F detector, which is the detector implemented in InfraPy, Los Alamos's infrasound processing software, works to reduce false alarms by adaptively accounting for background noise over time in order to adjust artificially elevated power or coherence levels due to high background noise. So what this means is you use this p-value here to identify your threshold for declaring a detection. When there's a time period with significant background noise, this actually elevates the power across your beam and leads to a large number of false detections. What we use is we use this C value, which characterizes the background noise across a time period of interest. And with the C value, we're able to remap the observed F statistic back to the theoretical F statistic. And by remapping that, you'll see that we really reduce our detection area, which effectively removes false alarm detections due to correlated noise from our data set. The second detector we're going to be looking at is the multivariate adaptive learning detector, or the MALD, which is implemented in Bloodhound. Bloodhound is Sandia's infrasound processing pipeline. And so this is a similar detector that's used to identify long-range infrasonic signals. And the way that the MALD works is it uses an adaptive background noise distribution to account for elevated background noise across 3 distinct time windows. The difference between the MALD and the adaptive F detector is that in addition to detecting signals with high coherence, the MALD also identifies signals with stable back azimuth estimates. So we're able to produce a detection data set that's based on a combination of highly coherent signals and signals that were perhaps not as coherent as we would like to see, but they have a steady or consistent back azimuth um, estimate. And so we have at the end, we have this data set where we've detected both types of signals. Okay, so our goal here is to produce a direct comparison between these automatic detector outputs. We'd also like to estimate how well each detector performs. In order to control this, we perform detection utilizing a common set of parameters for both detectors. So this included a broad frequency band from 1 to 5 hertz, a 30-second window length, and 2 different p-values or power thresholds for detection. These parameters were selected based on previous studies within our region of interest. So before we start looking at detection results, I want to highlight that the main driving factor of this study is that we do actually not know what sources we are going to detect. So we're likely identifying 2 types of signals, both of which can be seen in this figure on the left. First, we're likely identifying some sort of low frequency, persistent noise sources that are seen here in this constant back azimuth trend with low frequency values and very low signal power. We are also likely identifying more traditional infrasound signals that can be characterized by a high signal amplitude, a broader frequency band, a consistent back azimuth, and an increase in power. So the real goal here is to evaluate if both of our detectors are identifying the same signals, or if there are patterns where one detector consistently detects a noise source that the other does not. So after we ran this virtual processing experiment across the state of Utah, what we ended up with was 3 months of detections produced by our 2 detectors. So now I'm going to move from discussing things in terms of the adaptive F detector and the MALD to discussing them in terms of InfraPi, which is Los Alamos's software, and then Bloodhound, which is Sandia's. So you'll always see results from InfraPi in blue and results from Bloodhound in green. And so when we start looking at these detection results across the network, you'll notice a couple of different things. First, when we look at the total number of detections, you'll see that Bloodhound identified many more detections or many more signals than InfraPi did, except for this one station NOQ where the pattern is reversed. The second thing that we do is because we've been detecting across arrays, we have back azimuth estimates of each of these detections. And so we can use these initial back azimuth estimates to evaluate if the detectors are identifying the same signals or not. And so when you compare the back azimuth estimates, you notice a couple of interesting trends where in general, both InfraPi and Bloodhound identify detections from the same region of interest directionally, but then you see this discrepancy here where Bloodhound is consistently identifying signals from this direction, but InfraPi really isn't. And we see this pattern across all of the stations in our network. And then we see this pattern reverse at NOQ, where here Bloodhound and InfraPi are identifying signals from these sources, but InfraPi is consistently identifying signals from this source or from this direction. So we needed some methodologies to begin assessing and comparing our results. Our solution was to utilize a human analyst in order to begin identifying true signals. We felt that 3 months was an overwhelming amount of data for an analyst to practically look at, so we started looking at 2 hours of data. And our process here was that the analyst reviewed the waveform data and declared a detection when there was either a significant increase in power, as shown here, or there was a consistent back-azimuth trend, as shown here. We're then able to compare our automatic results to the analyst detection dataset and begin to classify results as either true positives, false positives, or false negatives. So true positives can be defined as detections where both the automatic detector and the analyst identified the same signal as seen in this overlapping section here. False positives are detections where the automatic detector identified a signal, but the analyst did not. These can also be considered false alarms. False negatives are detections where the analyst identified a detection, but the automatic detector did not. These can also be considered a misdetection. So below, you'll see two examples of this classification methodology where we see signals overlapping in time and based on their back-azimuth estimate, and we're able to label each of these detections based on our labeling schema. And so the overarching goal here is to produce measures on how well each of these detectors perform. So we can use these labels that we produced in the slide prior to calculate two metrics for evaluation. These metrics are recall and precision. And so you'll see that we use our series of true positive, and false negative detections to produce our estimates of precision and recall. So recall can be interpreted as the percentage of total relevant events correctly identified by each detector, while precision can be interpreted as the percentage of detections that are relevant. So for comparisons, precision is really seen as a measure of detection quality, while recall is a measure of detection quantity. So we can compare intersections between these three data sets, the two automatic detection bulletins and our analyst detection data set, to produce precision and recall rates and evaluate if both automated detectors are identifying the same signals. So here what we've done is we've produced overlaps of how all of our signals that depend on are based on the color here. And so you'll note two important things. First, there are very few signals that are actually identified by all three detectors. And second, you'll notice that there are a large number of false positive detections, particularly using Bloodhound. And so these two things contribute to really low rates of precision and recall. And so one thing that we looked at when we were thinking about this is we're pretty disappointed at how low these precision and recall rates are. But one thing we noticed is that there were a large number of signals that were identified by both InfraPi and Bloodhound, but not the analyst. And so this raises a really important question in detection theory that we've always had this assumption that the analyst is always right. However, our low recall and precision rates, coupled with these number of signals that were identified by both automatic detectors, but not the analysts, suggest that perhaps this is an incorrect assumption. And these results indicate that automated detectors may be able to identify low amplitude signals that are invisible to the analyst's eye. So if we consider these overlapping signals to be true positives, we are able to significantly increase both our recall and our precision rates across the network. So moving from this realistic data set, we wanted to start validating our results with synthetic data. So for this part of the study, we utilized a hybrid approach to synthetic data, which combined realistic pink noise with synthetic signals, and we used 4 relative noise levels in order to supplement our processing results. So we use these 4 noise levels in order to investigate how well each detector adapts to a changing background noise and how well it performs in high background noise environments. So you'll see on the right at that as the noise level increases, the signal to noise ratio decreases. And throughout this data set, we used a combination of short and long duration signals across a variety of frequency bands. And this was to compare how well each detector is able to identify these different signal types. So we first compared results produced using a p-value of 0.1 at both detectors, which is similar to our results from the realistic data. An important thing to note here when we compare performance is that InfraPy is able to identify almost all of the synthetic signals, while Bloodhound is not. And in addition, Bloodhound performance varies as a function of noise level, while InfraPy's performance remains constant. We can split this up into how well each detector identified the short duration and the long duration signals here, and note that Bloodhound particularly has issues identifying these short duration signals. So in order to perhaps improve these results a little bit, we utilize some parameter manipulation, and we increase the p-value for processing for Bloodhound to 0.3 over 0.1. And by doing this, we're able to increase the number of short duration and long duration signals identified by Bloodhound. And this significantly raises the performance of Bloodhound across all 4 noise levels. So we can repeat the same procedure that we did before and produce these direct comparisons of how well each detector identifies signals. And we both note that both detectors generally identify the same set of detections with no false alarms. So particularly this point of no false alarms leads to high levels of precision and relatively high levels of recall for both detectors. You'll see that recall for Bloodhound is much higher when we use this p-value of 0.03 over recall for the p-value of 0.01. So to conclude, this was a little bit of a pilot study that was focused on novel ways to compare infrasonic detection catalogs. We've done a couple of things. First, we've successfully produced a methodology to combine automatic detection catalogs with an analyst review to evaluate performance in terms of precision and recall. We've established a base detection baseline using real data and determined that InfraPy produced with the detections with the adaptive F detector is more precise, while Bloodhound produced with the MALD has slightly better recall. So in practical terms, this means that InfraPy produces a higher quality detection data set with fewer false alarms, while Bloodhound is able to overall detect more signals at the cost of introducing a larger number of false alarms into the detection data set. We've demonstrated that automatic detectors may be able to identify small amplitude, low signal to noise ratio events that cannot be identified by analyst review, and that ensembles of detectors may be able to potentially be used to provide a form of ground truth that's alternative to a time-intensive analyst review. And so we've also supplemented our results with a synthetic data set. The results from this suggest that utilizing equal parameters for comparing detectors may not be the best approach, as we were able to produce the most equal comparisons using different p-values for each detector. And finally, we've demonstrated that detector performance is reduced at higher noise environments where lower signal amplitudes can reduce signal to noise ratios below 10. In addition, we've shown that Bloodhound has more difficulty detecting short duration synthetic signals, which provide valuable feedback for continued detector development. Okay. So now that we've done this extensive comparison of these 2 detectors, we're going to use a series of known signals and ground truth data to evaluate conditions that affect detector performance. This study is really focused on evaluating physical properties such as signal strength, propagation path, and background noise, and the role this plays on how well we're able to identify a signal. So, like I said, the primary goal of this study is to quantitatively assess and interpret the detection performance of a regional infrasonic network utilizing data from GT data from UTTR in order to understand the underlying reasons for both successful detection and why detections are missed. The arrays within this network are located between 84 to 410 kilometers from the source, which offers the opportunity to examine automatic signal detector performances at distances within the acoustic shadow zone. This study was really motivated by a prior study by Jungyoung Park, where she utilized an automated infrasound processing pipeline to produce a year-long infrasound bulletin where events were formed based on 3 or more detections of a signal across the network. When we started comparing the bulletin to published blast logs from UTTR, which is the Utah Test and Training Range and is a major source of infrasound within the region, only 5 of the 47 UTTR events that occurred in 2012 were actually present in Jungyoung's event bulletin. So this discrepancy between the large number of events that occurred and the small number of events that are in the bulletin could reflect failures in either our ability to detect signals from UTTR, or it suggests that we have issues with either associating or locating signals of interest across the network. So we took this systematic approach where we said, okay, this could be related to detection, it could be related to association, it could be related to location. Let's start with detection and rule out if that's really where the problem in our processing is or not. So, like I said, we're going to use this set of 47 ground truth events to test our automated detector processing. The reason that we call these events ground truth is because we have a known source location, we know that it's occurring at UTTR, and we have a known origin time. They've told us what time they're actually setting these explosive events, pictured down here in the bottom off. So this allows us to predict when our sensors should record a signal from the source. These events also spanned 3 seasons, and while they're not evenly distributed across the seasons, this presents an opportunity to start looking at temporal detection dynamics. So how we started is we replicated automated detector processing from Jungyoung Park, and we were able to successfully identify a large number of the GTD events. So here I've plotted up the total number of automatically detected ground truth events out of 47 at all stations across the network. And you'll see that this ability to automatically detect events or not varies significantly with distance, where these stations that are between about 150 to 200 kilometers from the source are able to identify many more events than stations further or closer to the source are. So the outstanding question is, what about the rest of the events? Are our detectors missing these, or is there no acoustic signal coming from some of these events? And this presents kind of the guiding question through this study, which is that detections could be missed due to either a lack of an atmospheric waveguide, such that energy is not efficiently propagating from the source to the receivers, or there's high noise level at the receiver that's masking the signals so that we're not able to detect them. Or alternatively, it could be a combination of the two. So we began by modeling propagation across the network to understand why stations are not detecting events. So these figures illustrate ray tracing or propagation modeling for infrasound arrivals as a function of phase for 2 different GT events. And the black triangles indicate all of the stations within our network. So you'll note that the stratospheric, which are pictured in the green, and the tropospheric, pictured in red, arrivals vary across these 2 examples. And so that demonstrates how we expect the atmosphere to change as a function of time. And similarly, you'll also notice in this example here that arrivals are not predicted at a number of stations within the network. So the combination of this modeling provides the ability to produce statistics on predicted phase arrivals as a function of station distance from source and season time of year. So here what we've done is we've plotted up as a function of distance what the percentages of our predicted signal arrivals are through the spring, summer, and fall. And so, based on known atmospheric dynamics, we expected stratospheric arrivals to vary across the vary based from season to season. And what's interesting to note here is that although we predicted stratospheric arrivals, as you saw in the ray tracing diagram in the previous slide, none of these arrivals are actually predicted to reach stations within the network. So our stations are predicted to primarily have tropospheric, shown in red, or thermospheric, shown in blue, arrivals. In many cases, no arrivals are predicted, and that's denoted here by the gray. So this indicates that events may not be detected because no signals are actually propagating from the source to the receiver. So next, we note that high noise across the stations could also cause these detectors to fail. So we began to examine seasonal noise across the network, shown here as the mean power across our frequency band of interest for at a variety of stations as a function of season and the color, and these are compared to noise infrasound noise models from the IMS network. And so we note that while these median noise estimates at each of the stations fall within the bounds of the IMS low and high noise models, our estimates are generally high across the network relative to these bounds. We also note that background noise peaks in the spring. So background noise is consistently higher in the spring at all 4 stations and decreases in the summer and the fall. And similarly, you'll see that these noise levels vary across the network, where noise is much higher at LCM than at BRP or FSU. So this combination of initial propagation modeling and our noise analysis suggests that we should be seeing arrivals at the sensors within the network. And the first step we took to look at this was perhaps our parameters for automatically processing detections need to be modified. So we took two approaches to this. So first, similarly to what I presented in chapter 1, we adjusted the p-value for detection across the network a total of 4 times. And the idea here was perhaps our parameters for automatically detecting events are not adequately tuned. So by changing the p-value, can we continue to identify more signals of interest? So you'll note that shown by the colors here, red, green, orange, and blue, we are able to add a few detections across the network as a result of this parameter manipulation. Second, we performed an analyst review of the data to see if additional ground truth event detections could be identified in order to interpret and possibly improve the automated results. So the analyst review identified time periods where a signal of interest consistent with the ground truth information was clearly present in the time series waveform data, but unidentified by the detector. This represents an enormous benefit of using arrays because we know the back azimuth that a signal should be arriving from. So this allows us to check our array processing results. In this example here, the red line represents the true back azimuth from the source to the receiver. And so we can compare our signal processing results with this known back azimuth as a little bit of a gut check to say, okay, yes, this signal here, it's high coherence, we see the power increase here, and it has the right back azimuth. This signal is probably coming from UTTR. So as seen as in the purple section of this chart here, by performing this analyst review, we were able to identify a number of ground truth events that had been missed by the automated detector, but the analyst identified. So this indicates that our detectors are not identifying as many signals as we would like them to. So next we wanted to say, okay, so why are our detectors failing? Are they missing signals because of high noise? Are they missing signals because, as we predicted during our atmospheric modeling, there actually are no arrivals predicted to arrive at our station? And so the way that we do this is we performed a kernel density estimate, or KDE analysis, in order to quantify automatic detection performance in an integrated way by capturing the effects of both background noise and propagation path affected effectiveness based on continuous background noise assessments. So the goal of this analysis is to identify time periods where the beamed signal spectral amplitude is higher than typical noise levels, which would be due to high noise levels across the array, or when the beamed signal spectral amplitude is comparable to or below the typical noise levels. This would indicate that the lack of a positive ground truth event detection is likely due to unsuccessful signal propagation from the source to the receiver. So in these figures here, the green KDE represents the probability of noise amplitudes at the time of the event as a function of frequency. We marginalize the predicted noise amplitude distribution up to either the observed beamed signal, shown in black, or residual, shown in blue, the spectral amplitudes across this frequency band, and average our results to obtain a series of cumulative distribution values. These cumulative distribution values or coefficients that we've named C residual and C signal are bound from 0 to 1 and can be used to interpret how the spectral amplitude of a particular beamed signal and its residual compare to the background noise amplitude statistics represented in the noise KDE. So if a signal of interest is present, we expect the C sig value to be greater than the C residual value. When the C signal value is less than or equal to the C residual value, the beamed signal power is less than the measured residual, which suggests that the lack of an arrival is probably due to propagation effects as well as time dependent noise. So we can begin to compare relationships between these two distributions for each event in order to identify if missed signals are due to propagation or noise. So in this example, the low C residual values and the corresponding high C signal values indicate that this signal has high amplitude and occurred during a period of low background noise. And this actually corresponded to an event with a high signal to noise ratio that was easily identified by our automatic detector. So we're able to replicate this methodology across all of the misdetections at our network, and we end up with statistics on misdetections across the network. You'll see that we plot up these C residual versus C signal values, and we see a clear separation. And we're able to use this separation to cluster or identify if detections were missed due to high noise or due to propagation related causes. And you'll see that the distribution for these varies as a function of distance, where stations close to and far from the source miss more signals due to propagation, which can be expected given our known signal propagation patterns. So to conclude here, we've performed an extensive study of automated detector performance across a regional infrasound network, which benefits from prior knowledge of these ground truth events originating at UTTR. We note that automatic detectors do not successfully identify a large number of signals from UTTR, and that analyst review is necessary for producing a robust GT detection data set. The combination of automatic detections and analyst picks provides statistics on signal propagation across the network, where observed signals occur more frequently than what is predicted through propagation modeling. This suggests that the atmospheric models do not fully capture the variability of the regional propagation distances used in this study. We've shown that detection capability varies primarily as a function of distance from the source, and we've produced a methodology to separate causes for misdetection, and we have shown that successful event detection at regional distances is driven primarily by variations in wind conditions, which lead to high background noise across the station, or atmospheric conditions that affect signal propagation. So another way to think about this is that our detectors fail to identify low signal to noise ratio signals due to both high background noise and low signal amplitudes caused by attenuation when the signal propagates from the source to the receiver. So finally, we now have this really robust set of detections that have been verified by the analyst. And the question now is, can these detections be used to enhance our understanding of error within infrasound event localization? So As concluded in part 2, the high number of successful event detections across the network suggests that the lack of GT events in this Park 2014 bulletin may be due to failures in either the way that we associate signals or the way that we actually locate events, and not because we're unable to detect the signals. So this study focuses on the location of these ground truth events to explore problems in the automatic processing pipeline and identify improvements to location estimates based on model-based predictions. So throughout this chapter, we're going to be presenting or performing event location using this Bayesian infrasonic source localization methodology. This is a methodology that was developed at Los Alamos, and the way that it works is it combines likelihood equations for back azimuth and travel time constraints from your set of signal detections to assign a combined likelihood value for a source spatial location and time. Prior iterations of the Bissell methodology described infrasound propagation using a uniform celerity value, which essentially says that all signals should be propagating with the same speed or travel time. And based on what we know of infrasound propagation, this is an extreme simplification and is actually not the case. So recent iterations of the Bissell methodology produce an updated location hypothesis that is described by more realistic distributions for azimuth and travel time. And so there have been 3 major improvements to the Bissell methodology. In 2014, we began to develop this series of semi-empirical model-based priors to characterize propagation across a network. In 2015, we moved from these priors to stochastic propagation-based path geometry models to characterize propagation across the network. And finally, in 2020, we moved from this stochastic models to a generalized celerity model for the Western US. So what does this actually mean? So we have essentially 2 models that predict infrasound propagation across a network of interest. And we're going to be focused on producing comparisons between locations produced with these 2 models. So the first set of models that we're going to be looking at is these path geometry models, or PGMs. These are a catalog of models based on a season. So for example, these are path geometries from January, and you'll see they're binned into azimuth from source. And so they predict the probability where this really dark blue is highest probability and anything that is gray is no probability of observing a signal with a given celerity, denoted here in the y-axis, as a function of distance and azimuth from a source. These have been produced combining results produced through ray tracing through 7 years of G2S profiles across the Western US. And I'd also like to note that there are a similar catalog of models that predict back azimuth deviation. So we are able to predict how much we expect the back azimuth to deviate from the true back azimuth as a function of distance and azimuth from the source. So second, we're going to apply this generalized celerity model. And what this generalized celerity model is we essentially took this catalog of all of these predicted models and smashed them all together. So we've combined the potential of all arrivals at all of these azimuths and all of these ranges to produce a single dimensional model that weighs the probability of observing the 3 infrasound phases. So the main question is, which of these models produces the best location estimate and why? So in order to evaluate the different results produced by these 2 location models, we're going to use procedures from the seismological community to evaluate the errors associated with individual event locations. So we're going to be discussing results as a function of precision and accuracy, where precision can be evaluated as if the true event location is contained within the 90% error ellipse. I'll show an example of this on the next slide. And the accuracy is evaluated as the area of the 90% area ellipse, or the missed location, which is the distance of the event location from the true location. So here I'm going to show you two example event locations with a couple of important details. So you'll see that we've plotted up the locations where our locations produced with the generalized celerity model are shown in black, and the locations produced with the path geometry models are shown in dark blue. These different things that we're showing the maximum a posteriori source location. So this is the best guess for where the source is actually located. And then we have these 90% error ellipses. And this says that we are 90% certain that the event location is within this error ellipse. And then this red star shows the ground truth location. So you'll notice a couple of important things. One, in this location estimate, the 90% error ellipse for the event produced with the path geometry model does not contain the true source location, whereas in this example, both do. And second, you'll see this discrepancy where in this location, the event location produced with the path geometry models moves further from the true source. And in this example, it moves closer to the true source. And the last thing I want to point out is that you'll notice that these arrow ellipses are really skewed kind of towards the northwest southeast. And this is likely due to the distribution of stations detecting the events. If we look at the azimuthal distribution of detections across the network, there's this large gap where we have absolutely no detections. And so this is likely driving some of the bias in the way that our 90% error ellipses are produced. So what this means is we can use these different catalogs or methods to predict propagation across the network and account for signal travel times, but we're somewhat limited in our ability to reduce all bias given this network layout and the detection data set that we're working with. Okay, so we wanted to next start comparing individual event estimates, and we notice a couple of things here. So first, any event that's plotted with an empty marker indicates that the 90% error ellipse for that event does not contain the true source location. So this error ellipse, for example, would kind of look like this and not contain this red star. So using our metrics that I discussed earlier, this indicates that the precision of this location estimate is reduced. So second, you'll notice some patterns in these location estimates as you compare results on a monthly basis. So in general, the maximum a posteriori location estimates using the monthly path geometry model, so the blue estimates, trend to the northwest of the true source in the spring and to the south of the true source in the summer. And we'll also note that use of these monthly path geometry models for location increases mislocation errors by an average of 10 kilometers. We can also start looking at temporal estimates, and we see a really interesting trend here where location estimates produced using the generalized celerity model are early. They have negative origin time residuals, and location estimates produced using the path geometry models are late, or they have positive origin time residuals. So why are we seeing these results? Can these results be related to the models that we're using to predict signal travel time and back azimuth deviation? And the way that we addressed this is we started comparing observations, which are anything shown here in gray, the gray boxes, with predictions. And so here what we're showing on the left is what the predicted celerity distribution based on the path geometry model is for a given station and season. And you'll see that the observations really don't line up at all for both our celerity predictions and the extent that we expect a signal back azimuth to deviate from this source. So across these estimates, celerities are both under observed, which means that they're slower than what is predicted, or over predicted, so they're faster than the predictions are faster than what is observed. And like I said, the back azimuth deviation is greater than what's predicted. And we see similar results when we look at the generalized celerity model, where the model primarily predicts thermospheric arrivals, and our data consists primarily of stratospheric arrivals. So this tells us that neither model is effectively predicting propagation at these regional distances. However, in general, our location and origin time estimates weren't really that bad. So we began to discuss if there were ways that we could improve upon our estimates. And so what we decided to do is we decided to use our detection celerity distributions to put together an empirical model for both celerity distribution and to update the expected back-azimuth distribution. So this celerity model was computed by applying a kernel density estimate to the celerity values in the data set, and then performing a curve fit optimization to identify the three weights, means, and variances for the celerity distribution. So you'll see that now the model really represents the data that we see, where we see this really large stratospheric contribution, a pretty large tropospheric component, and then very little tropospheric arrivals. And we've done the same thing here, where we've plotted up all of our back azimuth deviation, and we've expanded the deviation across the network to 5 degrees. So when we produce locations using this model now that are shown in the green triangle, we notice a couple of interesting things. First, you'll notice that when compared to results from the generalized celerity model, the spatial locations don't change very much. And this corresponds to very little change in mislocation between the individual event estimates. Second, if you look closely at these figures, you'll see that the origin time residuals for events produced with the empirical model are very close to zero. This indicates that while we have not been able to improve upon spatial location error, by accurately accounting for the celerity distributions in our model, we've improved our origin time estimates. And so the last thing I want to say is, if you're a seismologist, you may be looking at this and saying, man, those are really big mislocations, but these are actually pretty good for infrasound results. So in general, we're really happy with our results. And so finally, to conclude, we've done a lot in this location study. We've applied metrics from seismic location to characterize infrasound location using a variety of celerity or travel time models. We've determined that propagation characterized by these path geometry models is optimized for stations further up from the source. So because the model really had such a big thermospheric component, it's really meant for stations that are located further than 500 kilometers from the source. And when we apply this model with our regional network where the stations are so much closer, we're both underestimating and overestimating signal celerity, which leads to large location errors. We've noted that the use of this generalized celerity model produces relatively accurate spatial results, but produces origin time estimates that are earlier than the true origin time. And finally, we've developed an empirical celerity model that produces spatial location estimates with similar accuracy, but improves temporal precision and accuracy. So this indicates that these models may have, improving these models may have significant impact on how well we are able to accurately identify a source of interest in time. So to finally conclude, we've gone through a lot in this past almost hour, and I hope that I have been able to successfully answer some of the questions that I posed at the beginning of this presentation. So throughout this presentation, we have demonstrated that by refining and testing automated processing, we can produce a broader understanding of network dynamics, noise conditions across a network of interest, and limitations of atmospheric modeling. We've produced an in-depth analysis of signal characteristics from surface explosions. We've produced summary statistics on detection and location capabilities, and we've produced direct comparisons between predicted and observed signal dynamics across a regional network. I've concluded throughout this that we probably need to continue refining our detection and location algorithms because we're really not able to identify signals of interest in high noise environments. And the distribution of our stations in this network really impacts our ability to detect and locate stations of interest. And then finally, while these advanced automated detectors successfully identify events with correlated background noise, further investigation is likely needed to understand and possibly adapt to changing noise environments. So that's all I have. I'd like to step through some conclusions quickly, or some acknowledgements quickly, excuse me. So this dissertation represents 4 years of hard work, dedication, and personal growth that would not have been possible without the help of support of numerous people. First and foremost, I'd like to thank Dr. Stump. I am so grateful for the opportunity to earn both a master's and a PhD with him, and he's given me so much support over the past 6 years. I'd like to thank my committee members, Chris Hayward, Heather Deshawn, and Robert Gregory for all of your time, encouragement, critique, and challenges throughout my dissertation process. I've been really lucky to have 2 bonus committee members who are Stephen Aerosmith and Josh Carmichael, and I'd really like to thank them for all of their support and their research expertise. It has been my privilege to complete the majority of my PhD work as a simultaneous graduate research assistant on the seismophysics team at Los Alamos. I'm grateful to my research members and external community members, Omar and Phil, for the opportunity. I joined the Geophysical Detection Programs team at Sandia National Labs during the home stretch of my degree completion, and I'm very excited about the opportunity and looking forward to what's to come. I'd like to thank Stephanie, who keeps the Earth Science Department running, all of the faculty, and my SMU grad student network, Monique, Sarah, Kimber, Erin, and Anastasia. And there are a number of grad students not associated with SMU that I would like to thank by name: Hank Cole, Alex Yezdi, Jordan Bishop, Devin Cole, Michelle Dunn, Sydney Deinbing, Elizabeth Berg, and Liam Toney. I would like to thank all of my non-academic friends who have supported me through this journey. Many of you are probably here for your first dissertation defense, so I hope I didn't scare you off. And finally, I'd like to thank all of my family, my husband, Brandon, my extended family who took me in when I was a new graduate student all alone in Dallas, my brother, Peter, my parents. My parents retired to Durango, Colorado the month after we moved to Santa Fe in 2016. Being 4 years away from them for the past 4 to 6 years has been one of the greatest gifts of my adult life. I am so grateful for the opportunities that they have given me throughout my life and all of their support throughout my career. All of this work is dedicated to my dad, who we like to call the original Dr. D. And with that, I would be happy to take any questions.
Hi, Francisca. This is Creighton Yap. I have a question, and I'm still processing everything I've heard here. So if you
Okay.
covered this, make sure you tell me. But going back to part 1, you talked about the analyst comparison with the automated detection business.